Hi guys, so in this video we're going to be going over formal charge. So formal charge is a part of the unit where we learn about Lewis structures, and it's basically a determinant of stability. So this is about covalency and energetics. And so the reason why formal charge is important is because sometimes structures may have more than one Lewis structure. So there are multiple examples of that. For example, the carbon dioxide molecule that we'll look at later, that one has more than one Lewis structure. And because of that, many times when we're predicting which structure will be taken, we need to be able to understand formal charge to decide which structure is preferred out of the 2 or maybe even 3 structures that are available. So formal charge helps us do that. It's a measure of stability. So a structure is more stable if the formal charge is closer to 0. So we can calculate formal charge with a simple formula, but let me first write down what it is. So it's a measure of stability of a structure and used to determine the preferred Lewis structure. Okay, and now we have a formula that helps us actually calculate the formal charge. So it's pretty much just basic maths, but there are a couple of rules that we'll go over. So the formula is V minus half bonding plus lone. So the minus encompasses the entire bracket. So it's the same thing as writing V minus half B minus L. And this is equal to FC, which we can say is formal charge. But we need to first define what V, B, and L are. So I'm going to just write down here. So V is equal to the valence electrons. So what that means is, for example, we know that nitrogen is in group 15 of the periodic table and has 5 electrons in its outer shell. So that means that V would be 5 if we're looking at a nitrogen atom. Then B refers to bonding electrons. So this is important. So bonding electrons basically means, for example, if we have C double bonded to O, well, the bonding electrons, if we're looking at the oxygen molecule, will be 4 because there are 4 molecules that are being bonded in between the C and the O. It wouldn't be just 2, even though the oxygen is giving 2 electrons. It will be 4 because all 4 of them will be accounted for. And it's not for bonding pairs either, because then otherwise we know the double line means 2 electrons for every bond. That means that bonding pairs is 2, but bonding electrons is 4. So keep that in mind. And then the last one is L. So L is equal to lone pair electrons. So lone pair electrons are basically the electrons that are not bonding but are part of the molecule. For example, if we have C double bonded to O, but we have these electrons over here, well, if we're looking at the carbon atom, there are 4 electrons that are lone because they are not bonding, and we have 4 bonding electrons. So that's important to keep in mind. Now, the reason I was referring to specific atoms is because when we're calculating formal charge, we calculate it for every element within the entire molecule specifically. For example, with carbon dioxide, let's say we took this structure over here with its configuration like that. Well, we would have to calculate the formal charge of the oxygen, the carbon, and then the other oxygen. In this case, the 2 oxygens would be the same, so we could calculate them together. But we'd have to add all the formal charges up. So for example, if the oxygen in that molecule had +1 each, and the carbon had -2, well, +1 -2 +1 again is 0. So we add up all the formal charges separately. And there is one more rule that we need to follow. We'll go over it when we come to the problem that I've specifically chosen, so that we can actually see how it's done. So let's move on to our first example question. So deduce which of the following Lewis structures of CO2 is more stable. So we've got 2 options. The first ones you've seen already, but the second one we have not seen. As you know, when you have an arrow on the bond, it means it's a dative bond, and that means that the carbon is giving 2 of its electrons to oxygen rather than sharing 1 electron each. So what we're going to do is calculate the formal charges separately. Let's start with A. So with A, we know that the oxygens have the same formal charge. So what we can do is just calculate the oxygen and multiply whatever value you get by 2. So oxygen. So let's start with V. So V is valence electrons. So oxygen is group 16, so it has 6 valence electrons. And then we minus it by half of the bonding. So the bonding is 4, since you've got 2 lines there that represent 2 electrons each. So 4. And you subtract it from the lone pair electrons. So you've got 4 lone electrons just sitting there that are not being bonded. So we're going to do 4. This gives us 6 minus 2 minus 4, which is equal to 0. But since we've got 2 oxygen molecules, we have to multiply it by 2 times 2. But that's still equal to 0. So 0 is our oxygen totals. Now let's look at the carbon. So we've got 4 valence electrons since carbon's in group 14. So 4 minus then half of the bonding electrons. So you've got 1, 2, 3, 4. So you've got 4 pairs of electrons that are being bonded, which means you've got 8 bonding electrons. And then you subtract that from lone pairs, which is 0. We got no lone pair electrons that are sitting over there. So this is 4 minus 4, which is equal to 0. So the total is 0 for the first oxygen, plus 0 for the carbon, plus 0 for the second oxygen, which is equal to 0. So already we can see that this molecule is very, very stable because the formal charge is very, very close to 0. We can almost be certain that this is going to be the more stable structure, but we should confirm with our other one, just to show you that it works. Now for the other structure, the oxygens are not the same. We're going to have to calculate each oxygen differently since you've got different bonding patterns. So let's say oxygen left. Let's call that the first one. So we've got six outer shell electrons. It'll now remain the same the entire time. 6 minus half of the bonding. So the bonding is 2 plus 4, 2 plus 2 plus 2, so 6. Because you've got 3 different lines over here. The dative bond still counts as 2. So minus half of 6. And then you've got lone pair electrons. So we've got 2 lone pair electrons over there, so we subtract by 2, which is equal to 6 minus 3 minus 2, which is equal to 1. So already, because this is not close to 0, we can already tell that this structure is not the best one. Now let's go into the carbon, which is in the middle. It's only 1 carbon, so we don't need to label that more than carbon. So carbon has 4 outer shell electrons, valence electrons, and half of the bonding. So it's got 4 lines over there, so that means it's 8 electrons that are being bonded. Remember, each line represents 2 electrons. And then we subtract it from its valence electrons. And in this case, we don't have any valence electrons. It's 0. So that means this is 4 minus 4, which is equal to 0. Now we can move on to the oxygen on the right. So outer shell electrons will be 6. 6 minus half of the bonding. So in this case, we've only got 1 line in between the carbon and that oxygen. So we're going to say that there are 2 bonding electrons. And then you subtract it from the outer shell electrons. And there are 6 outer shell electrons. So this gives us 6 minus 1 minus 6, which is equal to -1. So when we add these up, interestingly enough, we get 1 plus 0 and then minus 1, which is equal to 0. Now, you might think, oh, well, they're both 0, so that means that they're both equally stable. But the thing is that because individually on each of the atoms of the first example, they were all 0, they were all closer to 0, while in the other one, you've got one that's not 0 and another that cancels that out, but you've still got 2 atoms that are not equal to 0. That means that the first structure is more stable. When it comes to the same formal charge for each of the structures, you have to look at how close each of the individual atoms are. So we can say, let me just write it here. Structure A preferred. Let me circle that. All right, let's move on to the last example we have. So deduce which of the following Lewis structures of NO2 plus is more stable. And we've got A and B as usual. Now, interestingly, ions, so as you can see with the nitrogen, it would have lost its electron because it is less electronegative than the oxygen. However, we would still say it has 5 valence electrons when we're doing the calculations. So if you want to have a go at this, pause the video, but if not, I'm going to go straight into it. Okay, so let's start with structure A, and let's also acknowledge that these 2 oxygen atoms are different in their bonding patterns, so therefore we have to calculate them separately. So oxygen on the left. So outer electrons is 6 minus half of, so 6 remains the same. So you always look at the periodic table for the valence electrons. If you know the valence electrons, then you keep that there regardless of the ionic charge. So the bonding electrons are, well, you have 3 lines, so that means that there are 6 bonding electrons. And then you subtract it from the lone pair electrons, which is 2. So this is 6 minus 3 minus 2, which is equal to 1. Now we're going to do the nitrogen. So nitrogen has 5 valence electrons. We're going to ignore the fact there's a plus there that took away one of the electrons. Then minus half of the bonding. So the bonding, we have 4 different lines. So that means that there are 8 bonding electrons. And there are no lone pairs, so nothing to subtract there. So we got 5 minus 4, which is equal to 1 as well. And now we can move on to the oxygen on the right. So the oxygen on the right has 6 valence electrons, and you subtract it from half of the bonding, which is 2 electrons over there. Even though the oxygen has not contributed any of those electrons, it is still counted as bonding electrons. And then you subtract it from 6 of the valence electrons. So you get 6 minus 1 minus 6, which is equal to negative 1. So now if we add those all up, so FC is equal to 1 plus 1 minus 1, which is equal to plus 1. So that's the answer for that structure. Now the other structure, structure B, well, we can tell the oxygens have the same bonding pattern, so we can just calculate them together and then multiply by 2. So oxygen, so it has 6 valence electrons, and then you subtract it from half the bonding. So there are 2 lines, so 4 electrons are being bonded, minus the lone pair electrons. There are 4 lone pair electrons, which gives it a total formal charge of 6 minus 2 minus 4, which is equal to 0 for the oxygens. Now we multiply that by 2 later. Now we have nitrogen. So nitrogen has 5 outer electrons, and then it has got 4 lines over there, so that means 8 bonding electrons. By lines, I'm talking to these ones over here that show the bonding pairs. And remember that when we're counting lines, it only has to be the ones that are bonded to that atom specifically. So minus 8, and then you subtract it from lone pair electrons, which is 0. So you got 5 minus 4 minus 0, which is equal to positive 1. So even though they're the same, as we can tell, this one has, the total formal charge is equal to 0 plus 1. So 2 of these atoms are equal to 0, 2 of them. Whereas in this one, none of them are equal to 0. So even though they come to the same total, we can say that individually the atoms add up to 0 more in the second structure. So therefore, it is more stable. And generally, you won't see ions having a formal charge of 0 because the plus sign or the minus sign means that electrons are taken away, but they still get accounted for in the valence electrons. So typically those, the atoms that they've taken away electrons from or added electrons to will not have formal charges of 0. So that's how we deduced that structure B is preferred. Structure B preferred because more of the atoms had a formal charge of 0. So this is important to keep in mind that even if the formal charge is not the same, it does not mean that you can't choose a preferred structure. So that's it on formal charge. I hope that these questions gave a bit more understanding into how it works. It's really just basic math, and if you apply these principles as I have, then you'll be able to solve them easily. So in many exam questions, they might also ask you to practice, well, not practice, they might ask you to draw the 2 or 3 Lewis structures, and then they might ask you to find the formal charges of each of them and deduce which is the most stable one. So also, it's a very important thing that you get used to drawing Lewis structures because you will need them a lot, especially when it comes to formal charge and stuff like resonance and stuff like that. So we'll get into resonance in another video, but for now, thank you for watching and hope that this video helped you understand formal charge better.